This is my pre-submission seminar on design of variability aware low power. This is the technology scaling. If you look at the Murray law, every 1.5 years the transistor gets doubles. So to operate those transistors at the same time, to get low power, we should have the devices of small size where the voltage will get reduced. So this is what the video is mentioned over. As we go below this, I have run this 12 nanometer device. The power is voltage is less because voltage is a quadratic function of the power is a quadratic function of the voltage. So this is what as the technology is scaling down, the leakage power increases, which will be dominated dynamic power shown over here. My objectives are to study different techniques of ULP devices for modeling ultra low power devices. Devices stands for transistor, MOSFET. To propose better reconfigurable ULP devices and their circuits, modeling of proposed device and circuits in various technology of ultra low power, comparison of those devices for better. So if you look at it, 2005, I started the survey of 2005. The frying pan power getting architecture for FPGA architecture, this kind of thing is used where the circuit is divided into parts and the circuit which is not in use make off. This is a fine grain power getting taken in the use. In 2009, Johnson have also given some strip leakage technique in circuit level where the single transistor is added in the series which will be off if not required. Then adaptive biasing technique used for FPGA routing switches where the pass transistor logic but at 12 nanometer is circuit design. I have designed even the FinFET at the 12 nanometer. This is the 32 nanometer. If you look at all the previous one, the ultra low power even they are talking about, still they required the energy constant for moderate performance. So we have to change the geometry of the device at the same time. Some topology of the circuit will find out for good swing, and that will replace the ASIC. This is a summary of my work. The methodology I use the new devices. The new devices are FDSI, DG DG MOSFET, and on all devices I implemented the 2 pi gate with 2 FinFET. The devices has been checked with the process voltage temperature, that is called variability aware. This circuit has been device has been checked on process voltage temperature. The best performing devices observed the FinFET. Using this FinFET device, the parameters have been extracted, and this is the multiplex design and pre-voltage follower for analog application and non-digital application is design. Apart from this, the 4x4 multiplier has been designed with the different geometry devices of FDSI, FinFET, and MOSFET to see the performance of the circuit. And the 60 lamp cell, as the 60 lamp cell is the major part of the most of the applications, it consume 90%. These are the work on SOI devices in the low power technique circuits. At the same time, multiplier is designed as an application. Then the comparison of transmission gate CMOS technique is done for multiplier. One more topology is used, transmission gate. Three voltage follower on analog application is designed using pi gate from 12 nanometer. Design of multiplexer using pi gate from 12 nanometer. The devices that have been designed, the DG-CNP, DG MOSFET, FDSOI, and pi gate. While is a stacking on one, 2 gates are stacked. The function of the below gate is more than the upper one to avoid RDF. Then this single FinFET has been converted to multi-fin and the compare for high driving current. If you look at the device parameter, device graph, ITRS, international platform semiconductor, drain current is about this. If you look at 2018, 12.8. I have designed over here 12 nanometer rail gate with novel architecture by structure stacking, and this has been it was revised that door, so this parameter has been optimized. So modeling of digital application, the digital applications are 60 RAM, multiplier design, multiplexer design. The RAM is 90% overall, it consumes the area. So it requires more power. So we have to work on the stability and then the stable power structure of the SRAM side. 60 SRAMs has been considered with the FDSOI device. This is different geometry of the device. It is observed that the standby read-my write board, the stability is 349, 141, 685. It is good in case of the bulk SRAM systems. Similarly, for data potential voltage. For SOI device it is 70 millivolt, and for read it is 80 millivolt. For bulk RAM it is 140, more than that, and 280 millivolt. The PVD analysis has been done. Before that, the cell ratio is changed to see the minimum parameters, so that the area will be less and the power consumption will be less. As cell ratio increases, that stands for the area of the area increases. So it is observed that the static noise was, even though it is increasing, but power is also increasing. This is the stability during read and scan mode for supply voltage, variation in supply voltage. Supply voltage, open voltage is changed, then the stability increases. We have to work for the lower open voltage to get the optimized power. This is the word-like correlation, and the power consumed by SOI and bulk devices. If you look at, the bulk is giving good results, but at the lower technology, SOI is better. SOI is having better stability than the bulk. So this analysis, in this work, the stability of bulk and SOI SRAM is compared and found SOI SRAM is better stability than the bulk, even though the power is compromised over here. Data retention voltage also for SOI SRAM is good than the bulk SRAM, which is 0.7 and 0.9 for read and write, and for this is 0.1 for 140 millivolt to 80 millivolt. So cell ratio, if it changes from 1 to, it increases the stability, but area will increase. So it is depends on what kind of the power and stability is to be considered. But as a pull-up ratio is concerned, there is no effect on it. As far as multiplier is concerned, I have designed the multiplier in a Vedic style and conventional multiplier. Vedic technique and conventional technique is used for the 4x4 multiplier at number technology. And based on this is considered, and then they compare the transmission gate. So these are the basic architecture of 4x4 multiplier, conventional and the block. This is the average power versus supply voltage, delay versus supply voltage, ADP versus supply voltage. It is observed that this is a CMOS bulk device. It's a simple MOSFET with a CMOS technique. So here the Vedic multiplier, normal multiplier is compared. The average power of this bulk is called good over here, CMOS CL, with the carry loop head adder. Adders also, two adders are used over here. Ripple carry adder, carry loop head adder. So carry loop adder give better in this. Similarly, the delay of the carry loop head adder is also less, and VDP is the measure of the delay into the average power. Similarly, for temperature, the again bulk CL normally is observed good than the others for the all average power, VDP and temperature. This is about bulk devices, RC and UD. The variation has been checked, this process variation has been checked with the 1 sigma volt, and that's the 10% variations in the temperature, and say 1 sigma is used for the process. It is observed that RC is giving better result than the CLA normal. So in this case, the conventional multiplier CLA adder is having 45.4 less power than the other one. CLA adder is used in the multiplier, which is having 52.5% less delay than the rest of the technology, that is Vedic and the conventional. The Vedic and CLA, Vedic and RC, Vedic with RC. The conventional multiplier with the CLA adder is having 1.7% less energy delay cutoff. ADP is less in this way, so it is a good faster device, optimized device. This device is further compared with the another technology. This is conventional multiplier with the FinFET device and another geometry SOI device. These two different devices for normal. They compare here to observe that the FinFET device with the carry loop adder and conventional multiplier normally is a good in all cases. FinFET with this one is also FinFET with the carry loop with the change in temperature. So FinFET with the CLA normally giving good results. This is now being FinFET device with SOI, Vedic. The technology is Vedic. In Vedic, it is also observed that the FinFET CLA Vedic is giving good results. So FinFET CLA Vedic is also compared in the further part of this. So if you look at the FinFET CLA Vedic and FinFET CLA normal, with SOI CLA normal is compared, it is observed that the FinFET CLA conventional multiplier is giving good results in all this. So then this device is, this circuit is input based device, and can you look at this, the idle topology and conversion multiplier is considered to the transmission gate. So if you look at even the process variations has been done on this circuit, where these are really equal, but this has given very good EDG than the CLA value. So CLA normally is used for the multiplier. So this is the basic. So input based conversion multiplier CLA adder is having 25% less power than the others. Conversion multiplier CLA adder is having 5 minutes less delay than the others. Similarly, input based conversion multiplier CLA adder is having 10% less energy delay product than the others. So now this input CLA conversion multiplier when compared with the transmission gate based VDC and normal topology, there also the better results are observed in the input based CLA now. As a supply voltage variation is concerned, temperature variations are concerned, it is giving more than the others. But as far as this power is concerned, is stable. In process variation also, this input CLA normally is giving stable than the others. So temperature is very from 10%, sequence equal for Gaussian distribution, and couple is very plus 1. So this is the input device which has been designed priority in the device section. This parameter has been extracted and it is used to design the multiplexer, proposed multiplexer and compare the nanometer signals. These are the parameters that extracted from the TCAD. The device has been designed using this, and these are multiplexer using CMOS circuit multiplexer. Proposed multiplexer pass transistor, PGMOS, and multiplexer transmission gate. So this has given the good results over here. So yes, now it is around 14 nanometer. So this is very good. 12 nanometer. DRC has been done. This is the layout has been prepared for already. Previous information. Now analog application, VCO and free voltage follow. In VCO, there are 5 topology. Out of this 5 topology, the current rate topology is observed better in the case of the other devices. So these are the topology circuits for the oscillator. So this oscillator on this now the voltage is varying. It is change in the control voltage. It is observed that the current rate circuit is giving better stability. And this is the supply voltage when current rate circuit is giving better stability than the other. Similarly, for the changing chemical voltage, the current mirror is also stable. This is the graph. So 10% variation in supply voltage is observed the current mirror is 0% variation and 25% variation in the temperature. After switching place and topology at 12.20 and current delay is 6.7. So little bit temperature vary, but as far as the voltage is concerned, it gives very stable. The frequency is supposed to be a should not change in case of the supply voltage variation. Now these are the tables used for the using FDSI device on ISM band, 30 nanometer CMOS bulb, and this is the FDSI parameters used where NMOS and PMOS are used. So then variation has been considered. This is basic formula for TPH and TPI. Because frequency will change, this basically the when high to low, low to high will transit change. And this depends on the CL, KL, and this is UNC also the physical parameter of the device. If I change the device length, then again it will change. So parameter is going to change. These two, ultimately the frequency is going to change. We need a stable frequency oscillator. So this is compared with the CMOS bulb regulation. So this is the temperature that we show over here. So frequency versus gate length. So gate length K and KP will change. So if this will change, you will change of WNL in the process or mu in the process or the capacity. So ultimately the have frequency will change. So it is observed that FDSI is giving good stability over the range of the frequency being 2.48 to 7 gigahertz, that is the ISM band. FDSI requires 7 inverters to get this frequency. Otherwise, I consider 3 inverters, the frequency will be very high. That means we can get high performance circuit over here. CMOS is having even the power is less. But stability is considered 4 times better supply of stability, FDSI, 7 times better temperature stability in FDSI, and 2 times better process stability in FDSI. Free voltage follow. Free voltage current very nanometer technology is compared with using 12 nanometer. Basically, this is the total work on the 12 for the 12 nanometer. These are the, it should be the saturation always. So the wavelength is fixed. We have to calculate what W. So from this, the W has been calculated. The threshold has been considered. This is the cutoff frequency omega 0 has been considered. This is the transient response of 20 nanometer technology. This is the transient response of 12 nanometer. Frequency response is considered 7 gigahertz and 180 nanometer for the CMOS. For the 121 gigahertz at 12 nanometer, giving good frequency. So comparison is observed that the gain 0.75, 0.91. The gain for the 12 nanometer 3 voltage model is good than the CMOS model. So dispersion factor, the input voltage, some of the dispersion factor is observed over there in the input and the output. So in the output due to the Fourier transform. This can be reduced, but this is considered 0.6 volt. If it is increased, then the dispersion will increase. It has to be the offset voltage should be less. It should be considered less. That was at the 0.6 offset voltage. Temperature variation, the bandwidth will change with the change in the temperature. But the 12 nanometer is observed. Gain is also a little bit change. And 27 into 47 if the change in 121 gigahertz. But this is a good bandwidth. So you can work up to 47 gigahertz. Okay, this is the prepared DRS. Device design. Basically, I worked on the device of the transistor scaling the transistor. It is observed that the conventional MOSFETs today will not work at the below 32 nanometer. And conventional MOSFET they are good with the SOI. So conventional MOSFET, if it reduces the leakage current will increase. So we have to go for different geometry of the devices. So I tried for DC MOSFET, FDSI, FinFET, and out of that the FinFET has given the good result at 12 nanometer at this era of 3 years. So this is the first device in 2013 and that developed MOSFET with this LG 20 nanometer, offsetting is 1 nanometer. The beta element is considered the SiO2. It's developed MOSFET. Then VT is observed 107, ION is observed 158, ION is observed 4.16 microampere at 0.94. This is MOSFET. Similarly, the carbon nanotube is inserted into this area. This is called carbon nanotube based MOSFET. So here also the same parameters have been considered, but the VT is increased to 1.67. As VT increases, leakage current reduces, and the ION is nanometer. So the average, if you look at the ion-ion ratio is good in the lithium. But this is not reliable technology as on date, as CMPET is alignment is concerned and rest of the parameters. Another device is the double gate MOSFET and FDSI. Now here the dielectric constant is changed. Dielectric SiO2 is changed with the hydrogen oxide, HiO2, where the oxide thickness also reduces, and the results has been observed in the visual feedback. These are developing systems, IDVG characteristics of the device. This is another device FDSI with hydrogen oxide. This is compared with the standard. These are the bracket parameters of the standard from the ITRS. These are the simulated. So, what good results? ION for the FDSI is better than the DG MOSFET because the capacitor current, gate capacity is increased over here. And this device is given for the height of the patent. This is the novel structure introduced at 12 nanometer. Basically, the FinFET design using 1 pin and 2 pin. Simulation of resiliency analysis has been done. The parameter is matched with the standard parameters. The model file is developed. And the circuit simulation is done, that is the voltage flip, voltage follower, and the multiplexer. This is converted for 3D application with 3D. So this is single pin and single gate device. FinFET. So this is the dropping concentration. This is another wide gate. Another gate is used. This is having higher work function. As work function increases, the current reduces. Problem with the conventional FinFET, the current upside in SiO2 is replaced with the bulk silicon. Current leakage current increases due to the excessive period underneath the channel in the bulk. The question of buried oxide is very difficult, making the gate isolation from bud. The coupling issues are there with the film. So another refer this Schottky barrier refer. Metal semiconductor conduct having large barrier height and low doping concentration. Thus it reduces the RDF to the multiple. Thus the parameters considered for the FinFET. Bottom gate with higher work function. This is the cross section of your wide gate. The single pin is having iron 600. This is characteristic iron voltage. The iron IF current is 4500 for single FinFET. This is conventional FinFET. Single FinFET, single. Now in double fin, 2 pins are used over there. So the iron IF ratio increases to 10,000. All these things have been carried out in the visual figure of the mic. Now, as far as the bottom gate work function is concerned, if I reduce the bottom gate work function, the current increases. So, we have to manage the proper current to get the optimal solution for the device, so that the driving current will be good and the ion operation will be maintained. So, in this case, having the same parameter with all three devices, so 5 gate filter is in 10,000 ion and AF will also do that. So the pile gate filter is considered to gate in the fashion so that it looks like a pile of gate where it is to reduce the electron density under the channel. So the ion IF can be greatly lowered. Within pile gate structure, the substance region close to the feed can be linear accumulation condition so that the electron density can be lowered. The bottom gate is used with a higher work function to accumulate the area of the substrate. Pile gate structure is proposed to suppress the leakage current effectively without extra doping. Summary: by properly choosing the work function of the bottom gate, we can manage the IF current. So the lower bottom fields are near the accumulation node, so there will be less leakage. These are the publications done. Symbols of international conferences. Same effect interconnect also studied for the reduction of the short-term effect, design double gate center, double gate MOSFET, published there, accurate paper 2008 China, patent for abrasive filed in the office. Then the design of double gate MOSFET, abrasive hacking material for nanospecific, is present paper 14 at Thailand. It's international unicorn, this is also active controls, related to performance of area scaling 60 grams using SR MOSFET present in Thailand. The DCO is also presented in the IIT. In computer analysis of complex code, this is published in the international IGCA. Okay. Transmission gate box, PG box, and the novel box is designed, which is giving the good power. Voltage buffer having high stability and low static power, which is proposed in the voltage power. Also give the best technique from the bottleneck of the low power circuit for total application, that is DCO, current period. Today is for 6 times in, the standard has been changed to the 6 times in, better performance of SO is more natural. SO and the DCO is then for the active band from 2.4 gigahertz. Yeah, now we go. Discussion. Questions? I don't have this. First, your presentation, nobody wants to bring electronic to India. Right, so fast. So fast. Now, a few things, why another country? What are those portable applications? The voltage follower is generally used on circuits. Basically, look at the multiplier, calculator is a multiplier. multiply with the calculator. Calculator is one of the product application where the multiply has to be considered at the same time the voltage follows the step. You can carry it somewhere. So the battery life of that application.
Ask them what filter is. Yeah, for example, if we can have a movie, it's like a fish.
Feels like a fish.
Feels like a fish. On that tree, it can be operated make power loop for that as compared to the other. Filter is a type of material.
It's other formation below the oxide. If the SOI is another thing, SOI. Silicon. Which one is better? FinFET application or SOI? FinFET is better than this. Because the power consumed by the fins is quite controllable. It's controllable because fins are how many fins we can put it inside. So here, voltage free voltage follower. Voltage follower is basic building block of PC is also. For devices, the semi-pi is usual TPI. The parameter extent from that is matched with the standard PTL parameter of PTL, predicted model. And it has been modeled over there. SOI I use 45, 32 and 65 nanometer.
Yeah, but some of them are different from others. Why not take the same film? We have data for the same.
So this is the use of multiplier.
So if you are saying now,
that is
whereas if you see all the curves,
I analyze the FinFET device. On FinFET device, those are there in the case of this is what I have noticed in the FinFET device is finalized multi-phase, and on this there are if I didn't this was there. Here you will find this step. This is like 50 good. Steps to the 50 good. Submission is not given.
maybe up to 50. And you took some minus 3 dB frequency equal to minus 3 dB frequency.
Generally, we calculate the bandwidth at 0.7 of that. That is what minus 3 dB is. Minus 3 dB is considered for bandwidth. That is important.
You can do for others. How do you know the bandwidth is less, right?
So that always we should consider for minus 3 dB. Understand it.
Right, small b, is it correct?
Should be capital.
Not 1 dB. You have a definition for dB. I mean, what is dB? Express dB in terms of value.
It's dB. 20 log of the visual upon d.
Is there any other? What is dB?
Video. Output link. Base. No. No, base. No.
You have other base also, no?
Yes, easy.
Emoji or something else?
I can. Below that, minus 3 dB. Whatever the maximum voltage is,
Physically.
the uplink voltage is 5 volt. The voltage is 5 volt. So below 5 by root 2 is the minus 3 dB. So that much will be the below that there is no limit level of the circuit.
Physical meaning of I can call it as plus 3 dB. Physical meaning of
In performance of the circuit is
plus 3 dB. Physically, it doesn't mean minus.
About the range of whatever
it's the maximum one. It should be
Oh,
allowed.
it's not.
yes, about existing only the balance.
Comes to minus 3, not plus 3. Would be always log of minus 1 e raised to power minus of something will be 3 dB.
Negative consider.
What we are doing is logarithm and gain around the all these are mathematics. Logarithmic of 1 by root 2 is root 3 dB. Logarithmic of 1 by root 2 is 3 dB. Because their leading fraction is below 1. That's why below 1 means it is always negative for logarithm. That's why consider minus 3 dB. Then this is nothing but half of the power. power means 1 by root 2 or 1 by 2. Then we make 20 into 1 by root 2 log of 1 by root 2 into 3.
Right? Fourth one is like,
Between 750 milli.
that's what you will make 157. It should be 8 point. This is right, 0.15. It's also 0.157. Not right 157. I would say it should be 0.157. That is the last one.
Because there is the standard current is 1.1573. All the current is ion. With this sum parameter, second option is standard. Actually, this is what the result I have received against this.
So simulated your POX 0.98 compared to your standard.
Yes.
That is 0.98. Next one BTD 0.65, 0.65. BTH 0.3, 0.298. That's all. Now I R. Now tell me what it means to you. 0.16 in bracket 1/73.
This is what the receipt real I got.
That is your simulated value. What is there in the bracket?
Standard.
What is that?
So standard value it is
Is it 0.1573 or 157?
standard value 0.1573 and you got
It
0.16.
is in a different unit. Not that controlling.
Yes, exactly.
Otherwise, it is like simulation is wrong. But fourth, there is some problem. Last one.
Yes, sir.
Some problem. All that I see from the your simulated value is not matching with the
IPRS order. IPRS is the predictive. We can make it better over there. I of is 100 in the ITRS. I got it less than that. Yes. I got less than that, but given. So here, if you look at the threshold voltage is 0.298 standard.
first we have got
I made for
first
service.
is all problem is there. You don't know.
Look at it. You can see FDS standard one.
You see 1200. Here is same area. 1200.
1200 micro. 1.2 milliampere. 1200 microampere.
That is so.
What is standard? 153.
1.5.
So you could get
1.5.
and also same. Problem. But you look at that. Many of the figures, the jets are. You should tell what they. So, temperature, you can say. How do you relate to unlock device?
Analog and digital is two applications are. And the device is going to send parameters.
Two different.
Yes. Digital is at least we should go for digital and area address we can see in the analog for 10%. Analog is also used in the circuits, the voltage follow, the basic building block of any circuit. And digital circuits requires even the voltage follows.
So far,
In future. Now even if you look at even the printed technology, still more work should be go on circuits. For ultra power, the devices modeling has to be go beyond the because power is the quadratic function of voltage. If we go the channel length less than 12 also, then the voltage, working voltage will get reduced. So device will work very fast. So high performance has to be considered in that. High performance, we can make it more high performance, high frequency, faster working. Circuit topology has to be properly built based on the inputs.
What are the issues if you realize this simulated work?
It's lot of time.
Suppose if somebody wants something to implement,
Fabrication process is the issue. At level we have done. 65 lithographic process is used general value, 65
but do you think next 2 years? Yes, awesome.
now it is already reached to the 22 nanometer. So next 3 years it is at 65, using 65 lithography. So work is also going on in the same area existing fabrication lab.
By 2026 you saw that it can go to
Complete fabrication process and lab has to be changed. The IIT 300 nanometer.
So now you should have questions. No question in that. Go ahead. Suggestions you give. Purpose of the free submission is that lecture also. All advantage you have said about demerits.
Drawback of input. Basically, fields, if you increase the number of fields, then only you get a good driving current. So, depending on the number of fields, application process is the biggest. Number of fields alignment. Field alignment and gate alignment is the basic drawback. Fields and gate alignment. Getting the alignment of the gate with the field, that will be the product will limit.
Next, somebody wants to improve further. You can't go beyond some.
Where to add some spaces in between. Spaces. That will give the improvement.
Spacer is a brand bigger than targeted application. Targeted application.
Voltage control for same time the voltage for the basic building block. As I said, in FPGA there are so many blocks, PCL, recursive logic block. So in FPGA you have to work on the either 6-pass transistor logic where these switches. So I made it only that circuit to be reduce the power so that it is implemented properly in the complete thing.
Question is now, should we change the kind of this is? If so, what is the solution? Now we are not going to change. I don't know the rule of the game. Suppose you are permitted to change. That leads to the vision. Vision to vision. Now I am looking at vision. So, if you are writing, I personally use this. Don't write bulleted system. Write bulleted. Don't give numbers like that. Give bulleted 3. Good 3. Very spectacular. Anything. Striking. This. By this I must. I had an objective to make this my research. These objectives are met. These are the outcomes. Therefore, just suggestions. When I are a teacher, say that would be the, if you write too many, I don't know which one is the important thing. Which one is the outcome of your thing. Some automatically you can leave them also. If you unlock them, this conclusion should be very, very important. Each paper has letters. What you are not trying to do is you think you are data. That's easy, right? There are more questions? Then let us thank Sanjay. All these things are either legend, all these that is going to your jatara. This is your children, grandchildren. All the best friends, evaluate both. And they are proud of not easy. They medicine. All the best.